All right, this is Unit 7, Lesson 4, Graphing Sine and Cosine Functions. So our lesson essential question is, how can you identify key features of sine and cosine functions? At the end of this lesson, you'll be able to create and use graphs of sine and cosine functions. Example 1, understand the graph of a periodic function. A, what is the period of the graph of y equals sine x? So a periodic function is a function for which the outputs repeat after a constant interval of inputs. When a function is periodic, f of x equals f times x plus p, where p is the period. To understand the period of the function, you can use a table of values with radian measures on the unit circle to graph y equals sine x. Use the slider to explore how the graph of y equals sine x relates to the unit circle. So here's my table. So you can see at pi over 2, I get to 1. When it touches pi, I'm over here at -1. And it's going to go below. At 3/2 pi, it again touches -1 on the y-axis. And then at 2 pi, it's back to where it started. Because remember, a circle is 2 pi around. Right? And then it continues in that pattern. So it crosses here at pi, crosses at 2 pi, at 3 pi. So it crosses at every pi, and it goes above and below the x-axis. Notice that the y values begin to repeat themselves after x equals 2 pi. For this periodic function, sine of x plus 2 pi equals sine x. The period of the function y equals sine x is 2 pi. So it repeats after every 2 pi. What are the other key features of the graph of y equals sine x? The midline is the horizontal line halfway between the maximum and minimum points of the graph. So in this case, for sine, the midline is the x-axis. The amplitude is the distance from the midline to the minimum or maximum value. So from here, from the x-axis all the way to the top, in this case, 1. The amplitude of this function is 1. The minimum and maximum values of -1 and 1 occur at 3 pi over 2 plus 2 pi k and pi over 2 plus 2 pi over k plus 2 pi k. So you can see the first one occurs halfway between 0 and pi, which is pi over 2. So that's my maximum, plus 2 pi over k. 2 pi k. Okay. So basically I have this point and then I add 2 pi, which gets me to my next amplitude, which gets me to my next amplitude. Notice that they're always between. So if I added 2 pi plus 1/2 pi, I would get 2.5 pi, which is where my second amplitude is, or my second maximum point is. My minimum point falls at 3/2 pi. So it's between 1 and 2 pi, so 1.5 pi or 3/2 pi plus 2 pi k. So if I added 2 pi to that, I would get 5/2, like I would keep going, 5/2 pi, so on and so forth. The domain is -infinity to infinity. Okay, the domain, remember, is my x values. So the domain, it goes on forever to the negative x, it goes on forever to positive x's. Okay. And there are infinitely many zeros occurring at every integer multiple of pi. The range, remember those are your y values, are -1 and 1. The graph of y equals sine x has a midline at y equals 0 and amplitude of 1. Which is also, y equals 0 is also the x-axis. All right, let's try it. What is the period of the function of y equals cosine x? Okay. So very similar to sine of x, cosine x is also going to have a period of 2 pi. But I will actually go ahead and graph it for you so you can see it. All right, so I have y equals cosine x. So I can see if I can change it. So I can see that the top of my curve is at 1, The bottom of my curve is at -1, so that's going to be my range of values. But I can also see that it starts to repeat. Okay. Now it starts up here, comes down, goes back up. Okay, so this is going to be a period of 2 pi. So I'll graph sine y equals sine x, just so you can see it. So here I started at 0, I ended at 0. You can see that's 2 pi as well. So 0, 1. Here we are at pi -1, 2 pi over 1. Okay. So our period is 2 pi. So our period is 2 pi. For B, what are the other key features of the function? So as we saw, the domain is all real numbers. The range is from -1 to 1. The midline is y equals 0, okay, or x-axis. And the amplitude is 1. When you're dealing with just sine or cosine, these are going to basically be the same every time. You don't do anything else to them. Okay, so sine, cosine, they all have domains of real numbers. They all have a range of -1 to 1. The midline is always y equals 0, where the x-axis and the amplitude is 1. Okay. Now, when we start adding in like y equals 1/2 of sine, those things change. Okay. But if it's just y equals sine of x and y equals cosine of x, these things stay the same, okay? All right, example 2, identify amplitude and period. What are the amplitude and period of y equals 3 cosine x? Okay, so notice instead of cosine x, I have 3 cosine x. So that 3 tells me that something's going to happen to my cosine function, okay? So graph y equals 3 cosine x and the parent function y equals cosine x. So the blue is the cosine function. You can see that the red function is y equals 3 cosine x. Notice the difference in the amplitude. Okay? So here I am at 1, here I am at 3. So that 3 tells me the midline still y equals 0. I didn't do anything to the midline. It's still there. Okay. The minimum values are at -3 and 3. There are 3 times that of y equals cosine x. So the amplitude of y equals 3 cosine x is 3, and the period is still 2 pi. I didn't do anything with the period, okay? I can drag the slider to explore the amplitude and period of other functions in the form y equals a cosine x. Okay, so here is 2, roughly. Okay, so there's 2. There's at 1. Okay, so that's normal. 2, notice the period's not changing. I'm changing my amplitude, but I'm not changing my period. There we are at 4, there we are at 5. So notice I didn't do anything. So this A, that is my amplitude. Okay. All right, B, what are the amplitude and period of y equals negative sine 2x? So as with other functions, the graph of y equals negative f of x is a reflection of the graph of the parent function over the x-axis. As with other functions, the graph of y equals f of 2x is a horizontal compression of the graph of the parent function by a factor of 1/2. So neither of these transformations changes the amplitude, or the amplitude of y equals negative sine 2x is 1. So remember that A out in front, that's what gave me my amplitude. So in this case, it's just a negative, but it doesn't actually change the amplitude because the amplitude is still the absolute value of the distance from the midline to the top or to the bottom, my maximum or my minimum. Okay? The period is compressed by a factor of 1/2. Since 1/2 times 2 pi equals pi, the period of y equals negative sine 2x is pi. Okay, so look at the graph. The function has an amplitude of 1, and the value of the functions repeat multiples of pi. Okay? So this blue, that's my normal sine function. And this purple is my normal sine function. Notice with the red, though, that it's got squished. Okay, so it's been compressed down. Now, all of that happens within pi, where normally it was with 2 pi, now it's been compressed down to pi. Okay. So let's try it. What are the amplitude and period of each function? So I have y equals 1/3 cosine 1/2 x. So my amplitude, remember that's the number out front, is 1/3. And then my period, period is 2 pi divided by 1/2, which is really like saying 2 pi over 1 divided by 1/2, which is really 2 pi times 2, which is 4 pi. So this 1/2 actually stretched my period. So my period is actually now 4 pi. So it was double the length. So if it was 2x, I would have it. So I'm dividing by 2. But this time I'm taking 2 pi and I'm dividing it by 1/2. For b, y equals 2 sine pi x. So again, my amplitude is the number that's out in front. So that's going to be 2. And my period is going to be 2 pi. This one's divided by pi because that was the number of x in the inside, which is really just 2. So my period for this one is going to be 2. All right, concept. Frequency. Frequency is the reciprocal of the period. So y equals sine x and y equals cosine x each have a period of 2 pi and a frequency of 1/2 pi. The function repeats itself one time from 0 to 2 pi. Okay, so y equals negative sine 2x has a period of pi and a frequency of 1/pi. The function repeats itself one time from 0 to pi. Okay, so that's what it's telling me. The frequency is the amount of times it repeats itself within that period. Okay, so for example, here's the red, that's my normal, or the blue is my normal sine function. Okay, so remember it repeats once from 0 from here to 2 pi, it repeats itself one time. Okay, in negative sine 2x, it repeats itself between 0 and pi one time. So that's the frequency. All right, example 3, graph y equals a sine bx and y equals a cosine bx. So what is the frequency of the graph of y equals 5 sine 1/2 x? So step 1, identify the transformations to the parent function y equals sine x. Y equals 5 sine 1/2 x. So 5, remember, is our amplitude. So that number out front is our amplitude, and the 1/2 is our period. Remember that the frequency is the inverse of your period. So in an equation of the form y equals a sine bx, the parameter a indicates a vertical stretch or compression. The parameter b indicates a horizontal stretch or compression. So interpret the parameters to identify the amplitude period of the graph y equals 5 sine 1/2 x. The amplitude is stretched to 5 times 1, or 5, and the period is stretched to 2 times 2 pi, or 4 pi. Remember, I take 2 pi divided by 1/2, which gives me the 4 pi. Sketch the graph. Divide one period into fourths. So here, okay. So remember, the period is at 4 pi. I have 1, 2, 3, 4 different points. Okay. Plot in order a 0, a maximum, a 0, a minimum, and a 0. So here's my 0, maximum, 0, minimum, 0. The frequency of the graph is 1/4 pi. The graph goes through period every 4 pi units. How does the average rate of change differ within one period of the function y equals 5 sine 1/2 x? So choose different intervals in between 0 and 4 pi. Remember that that's our period, so that's one length of periods. Remember, I took 2 pi divided by 1/2 to get that 4 pi. And determine each average rate of change. Okay. So from 0 to pi, so 0 to pi, I have the points 0, 0 to pi over 5. So 0, 0 is where I start. Pi over 5, pi to 5 is my next point. So I find the rate of change. I take 5 minus 0, which gives me 5, and pi minus 0, which gives me pi. So I have 5 pi. That's my average rate of change. Between pi and 2 pi, my points were pi, comma 5, and 2 pi, comma 0. 0 minus 5 over 2 pi minus pi is negative 5 over pi. Remember, 2 pi minus pi is just 1 pi left. Okay? So you almost want to treat pi as if it were a variable, so like x. So 2x minus x would still give me 1x, for example. Okay? Then I go from 0 to 2 pi. Okay? So that was 0, 0, and 2 pi, 0, which is 0 minus 0 over 2 pi minus 0. Which one you divide that, you get 0. And then pi to 3 pi. So those are the in-between rates. So that's pi minus 5 to 3 pi minus 5. That's negative 5 minus 5 over 3 pi minus pi. Should be 2 pi, negative 5 over 2 pi. And then 0 to 4 pi. So over the whole thing, 0 minus 0 over 4 pi minus 0. 0 divided by anything, or 0 divided by 4 pi, anything is going to give you 0. So the average rate of change varies between negative 5 pi and 5 pi. The average rate of change over the whole period is 0. Okay? So the average rate of change, all right. So for let's try it. Graph y equals 3/2 cosine 3 pi x. So remember that 3/2 is my amplitude, so that's how tall it's going to be. So it's going to be up here. So that's it. So 3/2 is really 1.5. So about there. Okay. That's close we're gonna get. Okay, so then I have 3 pi. Remember, we take 2 pi divided by 3 pi, which is going to give me 2/3. So that's my period. So 2/3 should be right around there. Okay, so that's about 2/3, it's right about there. So this goes through one period between 0 and 2/3. And so remember, our frequency then is just flipping this number. So I get 3/2. So our frequency is 3/2. This is what our graph should look like. Okay, so again, those points of 0.0 and 1.5 and 0.667 and 1.5. So remember, that's 2/3 and 1.5. Okay, so then I want to find the average rate of change of the function over the interval from 0 to 1. So I'm actually going to look at Desmos because they have nice numbers. It's easier to see. Okay, so I'm starting from 0, so I want this point and I want this point. So I'm looking at 0, 1.5, and 1, negative 1.5. So those are the points that I'm looking at. Okay, so I have 0, 1.5, and 1, negative 1.5. Okay. So remember, we want, in order to find the rate of change, I'm going to take negative 1.5 minus 1.5. Minus 1.5, put that in parentheses, and I'm going to divide that by the change of my x values, which is 1 minus 0. So this gives me negative 3 over 1, which is just negative 3. My average rate of change is negative 3. Example 4, develop a graph and an equation from a description. A math teacher has a clock centered at the origin of a coordinate system. Our hand of the clock is 5 inches long. So here's the hour hand. Graph the relationship between x in hours and y in inches between the horizontal axis and the tip of the hour hand. Let midnight represent 0h. And graph the relationship for the time between midnight and 11:59 p.m. Write the equation describing the relationship you graphed. So first we want to formulate. Consider the diagram of the clock above. Think of the horizontal axis as the midline. Okay. The tip of the hour hand starts 5 inches above the horizontal axis at midnight. So here it is at midnight at 0 hours, so 0:05. 3 hours later, it reaches the horizontal axis at 6 a.m. So here's the horizontal, okay? So like looking at this, if this were my midline, So this I start at 5. 3 would get me to 0. 6 would get me to -5. 9 would get me back to 0 again. Okay, so that's what I do. 0, 5, 3, 0, 6, -5, 9, 0, 12, 5. Okay. Now I compute. The function starts at 0, 5 for midnight, then crosses 3, 0 at 3 a.m. and 6, -5 at 6 a.m. The hour hand travels back up to 9, 0, and then at noon is at 12, 5, before repeating the cycle again to end at 24, 5 at midnight the next day. Okay. So you can see the cycle. This is going to start to form a function. So the graph has a y-intercept at the maximum value, so the equation is a cosine function. So y equals a cosine bx. The minimum and maximum values occur at -5 and 5 respectively. So the midline is at y equals 0 still, and the amplitude is a equals 5. Remember, the amplitude is the distance from our maximum or minimum point to our midline. The minimum value repeats after 12 hours. So the period is 12. 12 equals 2 pi over b, so b equals pi over 6. The equation describing the relationship is y equals 5 cosine pi over 6 x. Okay. So let's try it. The minute hand of the clock is 8 inches long. Graph the relationship between x in minutes and y in inches between the horizontal axis and the tip of the minute hand. Let noon represent 0, h, and graph the relationship for the time between noon and 3 p.m. What is the period? All right, so the first point we have is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 0, 8, that's our first point right there. Okay. At 3, it's back to this midline. So 1, 2, 3, it's here. At 6, it's down to 8 again, and a -8. And then at 9, it's back up to the 0 point. So it's going to look something like this. So you can see that this is kind of the function that you have. Okay. So my amplitude is going to be 8, right? So, and it's a cosine function. Y equals a cosine bx. Remember, it's a cosine function because it starts somewhere other than 0. Okay, we said our amplitude was 8, so 8 cosine bx. We still need to figure out what b is. So it goes back to where it started. So we complete one whole cycle at 12. So it's still going to be y equals, so 12 equals 2 pi divided by b. So b equals pi over 6. And we're doing this in minutes instead of hours, technically. So this would be 30 minutes. This would be 45 minutes. So it would be back up again at the hour mark, or 60 minutes. So the period is 60. Example 5, compare key features of two periodic functions. The equation for f and the graph of g are given below. How do the period and amplitude of the function compare? So I have f of x equals 4 cosine pi over 4x. So if I look at this, so I see that I'm starting at 0, okay, for my graph. My period is between 0 and 4. Okay, my amplitude looks like it's at 4. So find the period of f by dividing the period of the parent function by the parameter pi over 4. So 2 pi divided by pi over 4 is 8. Okay. I can find the period of g by measuring the distance from one maximum to the next. In this case, it's 4. For the equation, I find the amplitude of f by multiplying the amplitude of the parent function by the parameter 4. The amplitude of f is 1 times 4, or 4. Here I can look at it, and it's also 4. The two functions have the same amplitude, but the period of f is twice as long as the period of g. All right, so let's try it. How do the frequencies of f and g compare? Well, we learned previously that the periods are the reciprocals of the frequencies. So the periods that we were given for f, remember last time, so for period for f was 8, and the period for g was 4. So our frequencies are 1 over 8. So the frequency for f equals 1 over 8, and the frequency for g is 1 over 4. So 1/8 times 2 would give me 1/4. So the frequency, so the frequency of f is half the frequency of g. All right, B, what else is different about the two functions? Explain. So looking at them, if I were to graph this, cosine functions start wherever your amplitude starts. Most of the time it's at 1, but if in this case the amplitude's 4, so our cosine would actually start at 4. This one actually starts at 0, 0. Okay, so that means that they're actually two different functions. So this one down here is a sine function. But also because g has a shorter period than f, they have different x-intercepts. Concept summary. Key features of sine and cosine graphs. The general equation for a sine function is y equals a sine bx, just as the general equation for a cosine function is y equals a cosine bx. In both cases, the amplitude is the absolute value of a, and the frequency is b over 2 pi. The equation for the graph below is y equals 1/2 sine of 4x. The amplitude is the distance between the minimum or maximum point and the midline. So in this case, it's 1/2. The period is pi over 2, or the length of one cycle. The frequency is 2 over pi, because the function repeats 2 times from 0 to pi. The x-axis, or y equals 0, is the midline, which is halfway between the maximum points and minimum points. And that is the end of Unit 7, Lesson 4.